Okay, this is our third discussion topic in this series, modeled lysine and methionine flows versus actual flows. And as we ended up in the last segment, we're going to start this off by looking at some problematic amino acid product characterizations. And by the time we get through this, I think we'll have a pretty good idea of why problematic characterizations really matter. That's going to be the sole focus of this part of this particular discussion. There's a fair amount to cover, and I want to make sure that we give it the time it deserves, because it's extremely important when you start talking about trying to have a successful experience with the balancing for amino acids. So the way we're going to approach this, we're going to look at a case of manufacturing branding versus molecular reality. And we're going to do that on the methionine side. On the lysine side, we're going to take a look at why characterization studies are only valid if they're confirmed by on-farm results. Okay. Obviously, if we're consulting on-farm and we're formulating diets for a farm, whatever characterization protected amino acids been given, it has to work on the farm, not just in a controlled study. And that's because when you have erroneous characterizations of protected amino acid products, that makes it almost impossible to achieve the results you should be achieving from amino acid balancing, or possibly even any results at all. The last thing we're going to look at is a brief introduction to theoretical biology versus living biology. And this will be part 2 of this particular discussion. So we're not going to spend much time here. We're going to introduce some concepts and some ideas that we'll be covering in the second part of this presentation. Okay, so let's go right ahead and start with a case of manufacturing branding versus molecular reality. We're going to look at it this way. These are two products that we're looking at. I want you to focus right here on the degradation rates. The A1 fraction is the same, but the A1 fraction plays no role in it, and you'll see that in a minute. So the primary focus here is on the degradation rate of the A2 fraction. What I want you to look at is how different these degradation rates are. The difference between these two is saying that the protein in product B is degraded about 45 times faster than the protein in product A, the A2 segment. That becomes even more significant when we look a little closer at the rest of the characterization. Everything, all protein, is in the A2 fraction, and it's all methionine. Okay. Here are the issues with these characterizations. The product A characterization here will predict a significant part of its methionine as intestinal methionine. But if you look at product D, product B is going to predict very little of its methionine as intestinal methionine. So they're very different. If you were looking for an intestinal methionine source, you would say, well, I'll use this one. It's degraded much more slowly. It's in the soluble protein fraction. It'll flow faster. That'll give me my methionine. Here's the problem. Both of these characterizations are describing the same molecule. The same molecule. The only difference is that product A and product B are manufactured by two different companies. Okay. Here's a little more insight into product A. Product A is well known for the positive effect it has on butterfat content in the milk. That effect results from providing a significant degree of rumen-degraded methionine. which means that this characterization is completely inconsistent with that well-established demonstrated effect. That effect is far more in line with what you see here. From strictly a competitive and marketing basis, if the company that manufactures B felt that they could reasonably represent their product like this, they wouldn't hesitate for a minute to do so. But now you've got a methionine source characterized by one company that says, oh yes, we've got all kinds of methionine that arrives in the intestine, it escapes the rumen. And the other one selling the same molecule says, no, about 95% of it is degraded in the rumen. That's an issue. So let's look at this. Both characterizations are describing the same molecule. So both sets of values can't be right. They can both be way off base, they can both be wrong, but they can't both be right. Methionine at the intestine is critical to improving milk protein yield. And these differences in characterization that we just looked at, they make the difference between actually improving true protein yield, seeing no positive effect at all, or possibly seeing a reduction in protein yield. So the characterization is critical, because if you use a methionine source that's characterized incorrectly or inaccurately, based on the results you see or don't see, you could very easily conclude, I'm not sure amino acid balancing works, or worse yet, I don't think methionine has anything to do with it. From looking at methionine scarcity in lactating diets, which is what we did in the first discussion, when only conventional protein sources are used, and looking at the amino acid composition of milk protein, that it is genetically determined that it's fixed, it's very clear that real grams of NP methionine at the intestine has everything to do with it. So the true culprit here is if we're not seeing what we should see in a way of response, the true culprit is expecting positive yield responses from predicted NP methionine that doesn't ever actually exist at the intestine. Again, that's critical too, because cows can't respond to predicted grams of NP methionine that represent prediction error, because they don't exist in reality. So the difference between these two characterizations on a methionine source is extremely important and should be taken into consideration when we formulate diets for lactating animals. Okay, what about the lysine side? What about lysine characterizations? Okay, we're going to go back to 2012 and we're going to take a look at the Minor Institute study where they evaluated 6 different protected lysine products. There are actually 2 segments to the study. This is the second one where they were looking at mechanical mixing and the effect on loss of lysine during a 24-hour period. You can see, we'll just go over this generally and we'll come back to some of this. Roughly 10% was our lowest at 6 hours. At 6 hours, the highest with USA lysine was between 90 and 100%. Now, so let's look at that. We're looking at just the first 6 hours. That's important. So the lowest was 10%, the highest was approximately 100%. But this was an in situ study. So what was being measured was lysine retained in the Dacron bag. And there could certainly be issues with particle size and bag porosity. Small particles escaping the bag considered as lysine that was lost. And that could be an issue if, but only if, the small particles that leave the bag actually contain lysine. Okay, and there's no way to capture any of that here. So rather than get into the nitty-gritty of this, we don't have to. We can look at the moisture study and find out all we need to know. So we're going to forget this. And we're going to look at the moisture study. This segment of the study was looking at the effects of a high moisture TMR environment in terms of lysine loss from protected products in the bunk over time. So let's look at this. Agipro-L, about 1% at 6 hours. USA lysine, 6% or 55%, excuse me, at 6 hours. Let's look at the overview. The lowest loss in 6 hours was 1 to 2% of the lysine. The highest loss was 55% of the lysine. Now, this study didn't measure retained lysine. It measured free lysine in the water solution used to wash the sample. Okay, so there are absolutely no particle size or porosity issues in this segment of the study. The only way that lysine gets into the water is by leaching through the encapsulation coating. Okay, that's the only reason it should be there. So let's look at this. Let's look at how it was actually done. At each point, the contents of the bag were transferred to a strainer bag, pretty big pores, soaked in a 1 liter solution. Arginine was used to solubilize the free lysine. But here's the important part. That was the initial sample. Then the initial sample was subsampled and passed through a filter of 0.45 microns, small enough to trap bacteria. And then the assay for free lysine in the water was conducted on the subsample. So porosity of any bag makes no difference. This is just a strainer bag. It's to be able to get moisture in and moisture out. The subsample was where the lysine analysis was conducted. Okay. So let's look at what we're being told here. USA lysine, according to a study updated in 2017 from Chemin, gives USA lysine 42.5% bioavailability. We're going to look at a segment of how that study was conducted. What I want you to look at and focus on is right here. This is a description of how the protected amino acids. In this study, they did lysine and methionine, USA lysine and metapearl at the same time. But what I want you to see is how this was actually administered to the cows. The protected amino acids were mixed into 100 grams of grain mix, about a quarter pound, and placed in front of the cows for 10 minutes. Any feed not consumed in that time was collected and placed into the rumen. You should have a pretty good idea of where this is going here and why this is problematic. Because in this study, the protected amino acids were not administered in the way that products would be fed on a farm. Okay. I don't have a problem with their 42% bioavailability as long as you're feeding the product this way. The problem is no commercial producer is even going to have cannulated cows on the farm, let alone mix the protected amino acid products in a separate grain mix of probably a pound or less, put it in front of the cows for 10 minutes, then collect it and put it into the rumen. That's not what happens on a commercial farm. So in no way does this study address lysine losses from actual TMR mixing and exposure to high moisture TMR environments in the bunk over time. That's important because if you use this 42.5% bioavailability value and you apply it to the entire lysine load of the product, then the only place this evaluation will even be close to accurate is if you're feeding it on the farm the same way you fed it in the study. Okay? And you can see that's not what happens. What happens on a farm bears no resemblance to this. So if you use that bioavailability value and apply it to the full lysine content when you're formulating a real world diet, you will be substantially overstating the lysine from the product arriving at the intestine. And that is a huge issue. Okay, some general thoughts on what we saw here. The range of lysine loss in the first 6 hours among all these products is enormous. It's all over the board. Ask yourself this question: how likely is it that products like USA lysine showing high lysine loss are characterized in a manner consistent with those losses? You won't know unless you review the characterization studies like we just did with the USA lysine study. You've got to look at those because lysine and methionine are co-limiting in terms of protein synthesis. If there's not enough of one, the full supply of the other can't be used for milk protein synthesis, which means protein yields are going to be limited. Again, as with methionine, given the fact that the amino acid composition of milk protein is genetically determined and doesn't vary, it's extremely clear that real grams of lysine at the intestine has everything to do with protein synthesis. And again, the issue here is expecting positive yield responses from grams of lysine that never actually exist in the intestine or possibly don't have an appropriate complement of methionine. And it's all because cows can't respond to predicted grams of lysine and methionine that represent prediction error. If I'm getting an 80-gram prediction for methionine at the intestine and 30 grams of that is prediction error, guess what the cow is going to respond to? Okay. So that's our look at this. A couple more thoughts. If we go back to the Cornell characterization, we're going to see something like this. Okay, this is the partitioning on USA lysine. Approximately 10% A2, 90% of it is in the B1 fraction. Okay, the A2 fraction has a low degradation rate. B1 is even lower. This is similar to blood meal. So this is being characterized in a way that would make it, in terms of bioavailability and in terms of degradation over time, similar to blood meal. And that characterization completely ignores the lysine lost in the feed bunk under normal on-farm feeding conditions, just as reported on the moisture side of the minor study. Okay, let's go back and look at this a little closer. Agipro-L is retaining 98 to 99% of its lysine load over the entire 24-hour period. At 6 hours, it looks like it's about 1% in that area. USA lysine, on the other hand, shows the highest lysine loss at 6 hours. Okay, what are the implications of all of that? The implications are that the Agipro-L lysine load, the lysine, total lysine provided by the product, remains constant, which means there's high encapsulation integrity. The encapsulation technology works extremely well to contain the lysine. Here's the issue with USA lysine numbers. For the second 6 hours of a 12-hour feeding interval, which is what most people do, the lysine provided by what remains in the bunk is less than half the lysine load provided in the first 6 hours. And honestly, because of how significant the loss is at 6 hours, I think it's fairly reasonable to conclude that the lysine loss begins almost immediately. And that probably only about half of the lysine load total of USA lysine actually makes it into the rumen. And of what does make it into the rumen, about 60% is fully degraded now. It's important to understand that the way the Kemen study was conducted, the protected amino acid products were completely shielded from anything that even would begin to approximate on-farm feeding conditions. So this was as favorable as it could be for the encapsulation in the products. Even in that absolutely most favorable environment, still 60% of the lysine was lost by Kemen's own numbers. Okay. This is why we need to approach characterizations by looking at on-farm results. Those characterizations are only valid if they perform on-farm and produce the response they should be producing. If that's not the case, then there are some issues. And it isn't that amino acid balancing doesn't work or methionine doesn't have anything to do it. It's something going on in our characterization or our modeling. Everything has to be submitted to the cow. If the cow validates the characterization, use it. If it doesn't, you'd better look into it. Okay. And again, that's because erroneous or inaccurate characterizations make it almost impossible to achieve the results from amino acid balancing that you should be able to achieve, or any at all sometimes. So in commercial production environments, only cows can determine bioavailability, not models, and certainly not studies that bear no resemblance to on-farm feeding conditions. The cow is giving us the straight picture because the product and the modeling is going through an actual on-farm process to get to the cow. We formulate it that way. So she gives us the verdict. And that's why instead of being dependent on a model, no matter what model we're working with, whether it's CNCPS, NRC, the French system, or whatever it is, we have to feed the cow, not the model. You can see why. If I feed the model and I turn around and run that diet back through the model, it's going to tell me everything's perfect. But models don't make milk. Cows do. And the cow is the final word on the characterizations and the modeling. Okay, let's spend a couple of minutes with theoretical biology versus living biology. Let's just throw out some terms and things we're going to look at in the next segment of this discussion. Probably the most important thing to remember is that models are not cows. And conversely, cows are not models. Cows are under no obligation whatsoever to perform as dictated by a model. They are living biology, they're the real thing, and they will give you a true and accurate response, indicating what they really are getting and what they're not getting. Every model generates prediction errors. It doesn't matter what it is. And that's to be accepted. That's because we're dealing with a very complex metabolic system, and we just don't know everything there is to know about it. It's unlikely if we did that we'd actually put it into a system of equations that would account for every variation possible on an infinite continuum. Okay, so what we end up doing is we formulate diets with models, but we feed diets formulated with models to cows. So if our modeled formulate diets are not validated by the on-farm response, this is what we have to bear in mind. The cow's not the problem. Okay, she's just not the problem. The problem is that we're not providing the intestinal lysine and methionine that the model's predicting. That's prediction error. Okay, and the real issues lie with feed and protected amino acid characterizations that are inaccurate or unreliable or unrealistic, or modeling prediction errors, or both. My perspective on it is that it's probably both most of the time. So that's why we say that nothing is validated unless the cow confirms. Well, that's the end of our discussion at this point. If you'd like more information on this subject or related subjects, that includes actual on-farm experience with amino acid balancing, results from that, you can go to formulate2.com, which is Formulate2 website, or you can go to our YouTube channel, which is Dairy Cattle /AA Balancing. And our next segment, we're going to take a look at theoretical versus living biology. We're going to take a look at approaches to modeling. We're going to look at approaches to mitigating prediction error. And we're going to do that not at any real technical detail, but our approach to it is going to be very important to understand some basic fundamental principles that have to guide us in our thinking about all of this. So thank you very much for being with us. We appreciate you attending, and we hope to see you next time. Take care.